We want to talk about logarithms, and what logarithms are basically is they are exponents but expressed in terms of being equal to an exponent. So I know that might sound confusing, but essentially what we do is we take an exponential, all right, and we solve it for the exponent. That's what I'm saying. We solve it for the exponent. So we have the exponent over here, and then we have log base b of c. So what a log does is it essentially tells us the exponent that I have to raise the base to get this argument, whatever this is. All right, so I'll give you an example. Log base 10 of 100 is x. If you're trying to solve that, it's going to be 2 because 10 squared is 100, right? So basically what a logarithm is, it's an inverse operation of an exponential, okay? So in other words, if you're saying, but I guess it's really important to me that you understand that a logarithm is an exponent, okay? It's equal to an exponent because we're going to use logs to solve exponential equations, and we're going to use them to do things that involve then rules for logarithms, and those rules for logarithms are actually the rules for exponents. Okay, so all we're really looking for is what power, what exponent do I have to use to get the answer, and it's from the base's perspective. So log base 10 of 100 is x, means that x is 2 because the base 10 raised to the x, 2 in this case, 10 squared, is equal to 100. All right, so you can always write them back and forth. You can write the log as an exponential and then solve it, or you can write the exponential as a logarithm. So let's say, for example, I said that what is log base 3 of 9? Okay, well, you would say that is 2. Hopefully, you would understand that was 2 because, all right, and this is important, 3 squared is equal to 9. The base, 3, raised to that exponent equals that argument. That's the idea. Okay, so if I said, okay, well, then what's the log base 5 of 125 then? Well, it should be 3 because 5 cubed is 125. Okay, so logs are the inverse operation of raising something to taking a base and raising it to a power. It's the inverse operation. It brings the power back down out of the exponential, okay, and it solves for it. So that's the idea. That's what a logarithm is. And you can do this with any base, but there's really two bases that are used frequently. One is base 10. If you look on your calculator, you will actually see a log button, and that log button is using base 10. Okay, the reason that base 10 is used is because our number system is base 10, so we use base 10 fairly frequently. The other one that we use is ln x, and again, you will see that on your calculator. If you look on your calculator, that you'll see an ln button. All right, it may be above an e to the x button, but e is actually a number. It's 2.71828, and it goes on forever. It's an irrational number. It's like pi in that sense, but we're going to talk a lot more about e going into calculus. So as you go through math, you're going to see e more often. All you have to really know about it at this point is that it's the natural logarithm, and the reason it's called natural logarithm is because it appears in nature fairly frequently. You'll see this ratio, and it's the same thing as pi. It's a ratio that's just a naturally occurring number, and we can define it, and we can define it mathematically, and we will going forward into other classes and other courses. But for right now, you just have to understand that it's about 2.7. Okay, and it is pronounced ln of x. So you'll see log x if it doesn't have a base, and sometimes it will, but if it doesn't have a base, it's base 10. And if it doesn't have log, it has ln, ln instead, it's still a logarithm. It's just a logarithm base e. Okay? So sometimes people find logs very confusing. And there's a lot of times where people don't like logarithms or think they're really strange. It will help you immensely if you think about logarithms just as powers. They're just powers. They're just the powers. Okay? I know I said that 3 times. I meant to, because I want you to hear it. So if you look at this, log base 2 of root 8. So what we need to do first of all is we need to express 8 square rooted as a power of 2. We want 2 to what power? So we're going to take the square root of 8 and write it first of all as 8 to the 1/2. And then recognize that 8 is 2 cubed. So we're going to have 2 cubed to the 1/2. Okay? Again, logarithms are powers. So we're just looking for the power of 2. What is the power going to be? And it's going to be 3 over 2. Okay? So that answer then is 3 over 2. Log base 7 of 49. Well, that's 2 because 7 squared is 49. Log base 6 of 1 is 0 because 6 to the 0 is 1. All right, so base raised to the exponent equals the argument. Again, up here, base raised to that exponent equals that argument. All right, 7 squared is 49. And if you want to get into the habit of doing that, just to sort of check it, you can write it out as an exponential. Okay, so this is log base. Wait a second, there's no base. All right, so what we know is that that is base 10. So that this is going to be minus 3 because 10 to the minus 3 is 0.001. Okay, so that's the idea of logarithms. It's just finding the power of the base that gives you the argument. So this is 10, 10 to the minus 3 would be equal to that. So the answer is minus 3. Now, down here, we're going to change the x around a little bit and say, what about if x is here? Well, if x is here, what we need is to follow the same procedure, that 5 to the minus 3 then is equal to that x. Now 5 to the minus 3 is 1 over 5 cubed, and then finally 5 cubed is 125. So this is going to be 1 over 125 as my final answer. Here, we'll take the base, raise it to the exponent, it equals the argument. So x squared is 36. So that means x is 6. Okay, now some of you that are used to solving that would say, well, it's plus or minus 6. Yes, except it's not because logarithms don't have negative bases. And the reason they don't is because you can't have negative 6. When you square it, it gives you 36, but then when you cube it, it gives you negative something. And then when you take it to the fourth, it gives you a positive again. It alternates between negatives and positives. So we don't use logarithms with negative bases. All the bases are positive. Okay? So that's why I'm allowed to just say 6. Here, again, take the base, raise it to the exponent, and we get the argument. So x is going to be 64 to the 2/3. Okay, then we just have to figure out what that is. Well, 64, that's the cube root of 64, and then squared. Okay, we did some rational power stuff earlier. The cube root of 64 is 4, and 4 squared is then 16. So the answer is 16. X is 16. Okay, so that's the idea behind logarithms. The other thing you need to know is because bases are always positive, that means that logarithms are always positive. So you can't take the log of a negative number. In other words, I can't say, what's the log of minus 1,000? Okay? We say no and get angry at you. All right? And the reason we do is because 10 raised to anything, it doesn't even matter if it's a negative power, is still going to be positive. Base 10, positive base means positive answer. Has to. No matter what the power is. So it's really important to understand that. You can't take the log of a negative number, which is why you'll often see logs, if you look in textbooks, other things written with absolute values of x. Okay? Sometimes, as opposed to just x. Because they don't want you to take a log of a negative number. So if you type in the log of negative 1,000 on your calculator, it will tell you no in some fashion. It'll give you an error. So the other thing that we need to do with logs, we need to understand the premise that they're just powers, okay? And then because they're just powers, that develops us some rules for logarithms that are actually the power laws, right? When you are multiplying a to the m times a to the n, then you know you add the powers. This is that rule, but expressed in logarithmic form. So if you're multiplying, you're allowed to write it as a sum, or if you're adding, it becomes a multiplication, all right? Same thing with division. Remember your division rule. A to the m divided by a to the n would give you a to the m minus n. So logarithms follow those rules for power. So if you're dividing log of something over something, it becomes log of that something minus log of the denominator. So log of the numerator minus log of the denominator. And again, it's because logs are powers. Okay. Same thing here. If you have a power to a power, you would multiply, right? So if you have a to the m to the n, it would be a to the m times n. So here's the same thing. If you have m to a power, it becomes a multiplication. All right. So the rules for logs are not new rules. It's important you understand that. They are the rules for exponents, which you've talked about and which we've used. They are just expressed in logarithmic form. So if you're multiplying, you're allowed to make it an addition. If you're dividing, you're allowed to make it a subtraction, or vice versa. And if you're raising a power to a power, then you're allowed to make it a multiplication. Or again, vice versa. If you have a multiplication, you're allowed to make it a power to a power. So what we do with these is we actually use these rules for logs, just like we use the rules for exponents, to simplify equations, and also to solve equations that we couldn't otherwise. So let's look at a few examples. So here's log base 6 of 8 plus log base 6 of 9 minus log base 6 of 2. So what we're going to do, if we have an addition, we're allowed to multiply. And if we have a subtraction, we divide. So what we're going to do is we're going to write this as log base 6 of, and then 8 times 9 divided by 2. Okay? Adding, we multiply, that's why 8 times 9, and then if we subtract, we're dividing. So that gives us log base 6 of, and then 72 divided by 2. And 72 divided by 2 is log base 6 of 36. And then you should be able to recognize that log base 6 of 36 is 2, because 6 squared is 36. Okay, so our answer is 2. You'll notice, though, that that is not an answer you can come up with on your calculator unless your calculator allows you to put in base 6. Because your calculator only uses log base 10. Okay, so it's important for you to be able to sort of manipulate these into things that you can use. So that's the idea of using these rules for logs. Okay, there's a couple you can try. What I would encourage you to do is actually pause the video if you're watching the video right now and you've got your math book in front of you. Stop and try these, and then start the video again and you can find the solution. I'm going to go through the solution now. So if you look at question number 1, I'm going to take this guy first and this guy, and I'm going to write them using the rules for logs that say if you have a multiplication, you're allowed to write it as a power. So I'm going to write that as a power, and I'm going to write this as a power. Okay, what I'm doing is I'm bringing the 2 that's out front up and making it a power. Okay, same thing here. Then this guy doesn't have a power, so I'm just going to leave him as is. Then I'm going to actually evaluate these. So log base 3, 6 squared is 36. So this is log base 3 of 36 minus log base 3 of 64 to the 1/2 is 8. And then plus log base 3 of 2. And then again, when I have subtraction, it becomes division. So it's 36 divided by 8. And then a plus means I multiply, so times 2. So what I get is log base 3 of 36 times 2, which is 72, divided by 8. And log base 3 of 72 divided by 8 is log base 3 of 9. And log base 3 of 9 is 2. So that's my answer. Okay. This guy's a little bit different. I'm just going to do him right here because it won't take as long. I have log base 9 of x minus log base 9 of y. And then I'm going to bring up that power, so log base 9 of z to the 4th. And then all I can do from there is just write it. If I'm subtracting, I'm dividing. So I'm going to divide by y. And then if I'm adding, I'm multiplying. So it's times z to the 4th. But that's as far as I can go because those are all variables. So it's log of x times z, that's a 4, right? Z to the 4th. That doesn't even look like a 4 now. Let me try to make that look a little nicer. We'll put a 4 there. There we go. Over y, but that's my answer for that one. So again, we're just using the rules for logs, which are the rules for powers or rules for exponents. Just if you're multiplying, you're adding. If you're adding, then you're multiplying. You can kind of go either way. In this case, we're going with the addition, making it a multiplication, and with the subtraction, making it a division. All right. So then the last part of this is then how can I use these? Why do I even care about logs? Like, okay, I understand the premise, but what's the difference between, or I guess not the difference, but what's the usefulness of these? Why do I care? So you can actually use them to solve log equations. All right. And in this case, we have an example here of log base 6 of 2x minus 1 equals log base 6 of 11. What you can do is you can actually use the rules for logs to bring them together. In this case, you don't really have to in this example, because if you have log base 6 of 2x minus 1 equals log base 6 of 11, then you know that 2x minus 1 then has to equal 11, which means that 2x has to be 12, okay, and x has to be 6. But the other way of doing this, and we'll just do this as an example following the rules, because sometimes you do have to do these. Okay, you bring the logs together, and then you write them as a single term. So when I bring it over, then I make it a division. So 2x minus 1 over 11, okay, equals 0. So that's a single, then I write it as a logarithm made into an exponential, which means I take the base and I raise it to the power, and it equals the argument like we were doing before. So that means I'm going to write this as 2x minus 1 over 11 is equal to 6 to the 0. Okay? Which means that 2x minus 1 over 11 is equal to 1. And then I solve that. So that means that 2x minus 1 is going to equal 11, which means that 2x is equal to 12, and x is equal to 6. And as I said before, you don't have to follow this whole procedure for this question, because you can jump right to this part, 2x minus 1 equals 11, because you have log base 6 on one side and log base 6 on the other. Sometimes you don't, or sometimes you might have a number over here or something like that. So this is the sort of steps every time that work, but you don't always have to go through all the steps. Okay, so let's look at another example. Log base nothing, so 10, of 8x plus 4 is equal to 1 plus log of x plus 1. So again, we're going to follow the rules that we just laid down, or the steps. So we're going to take the logs and put them together on one side. So we're going to bring that log of x plus 1 over. And then we're going to express it as a single logarithm. So we're going to say log of 8x plus 4 over x plus 1, because it's a subtraction, so we're dividing. Okay? Then we're going to write that as an exponential. So what we do then is, this is actually base 10. We know that. So it's 10 to the 1 is equal to this. So that's going to give me 8x plus 4 divided by x plus 1 is equal to 10 to the 1. Okay, and then I'm going to try to solve that. So in order to do that, I'm going to say then 8x plus 4 has to equal 10 times x plus 1. Okay, I'm just going to multiply by x plus 1. So that gives me 8x plus 4 is equal to 10x plus 10. And then bring the x's this way. We'll bring the 8x over there, and we'll bring the 10 that way. So I get 4 minus 10 is equal to 10x minus 8x. So that means minus 6 is equal to 2x, which means that x is minus 3. Okay, that's my answer. And then what we do is we check for extraneous solutions. Now you might be saying, what in the world is an extraneous solution? What it is that sometimes when we remove the logarithm, we're going to end up with something that might be a quadratic, for example, or something like that. And what can happen then is the problem that we have for logs, which is that you can't take the log of a negative number, might be negated because we got rid of the log. So we have x equals minus 3. What we have to do is go back up and check to see, is that okay up in the very original equation, way up here? And we will notice very quickly that it's not. So in other words, if I put in log of 8x plus 4 and I put in minus 3, okay, that's going to give me log of minus 20. And I say that's not okay. That's not going to work for me. All right, and the same thing with log of x plus 1 over here. So we have 1 plus log of x plus 1. But if I put in minus 3 plus 1, that gives me the log of minus 2. And again, I say that I can't do that. That's not okay. So even though this is a solution to my equation from here and from here, okay, it's not a solution. It's an extra solution because it doesn't work in the original equation. What happened, if you're wondering, well, what do you mean? Is when we divide this, since they're both negative, the negative cancels out. Okay, so it works, but it doesn't work in the original function. So you always have to go back and check. And because it's my only solution and it doesn't work, I say the actual answer is that there is no solution. There's no viable solution. This is an extraneous solution. So it's a nice answer, but it doesn't work in the original question. Okay? So let's look at this. This one, we have log base 2 of x plus 3 squared equals 4, which means the logarithm is already all together. It's already single term. So we can go directly, as I've said here, to exponential form. To do that, you're going to go 2 raised to the 4th is equal to this. Okay, so that means that x plus 3 squared is going to equal 2 to the 4th. X plus 3 squared is x squared plus 6x plus 9. And 2 to the 4th is 16. So we get that. That gives me x squared plus 6x, and then I'm going to subtract 16 from both sides. So 9 minus 16 is minus 7, and that equals 0. Then I factor this as x minus 7, plus 7, and x minus 1 equals 0. And that's going to give me two solutions. Either x is minus 7 or x is 1. And then I check them because I have to see if they're going to be okay. All right, so I'm going to take the log. So we'll say check up here so you know what I'm doing. So I'm going to check the minus 7 first. So I go minus 7 plus 3 all squared. That gives me log base 2 of minus 4 squared. Okay, and that's log base 2 of 16. And that's 4. So that one works. Okay, because of the squared. And then what we're going to do is we're going to do x equals 1. So if we put in x equals 1, we're going to get log base 2 of 1 plus 3 squared. And that's the log of base 2 of 4 squared, which is the log base 2 of 16, which is 4. So this one also works. So in this case, we don't have an extraneous solution. We have two solutions that work. All right, so there's a few exercises here in terms of solving these. So we'll just do a couple of them, or maybe we'll go through all three. But the first thing we're going to do is I'm going to put together log base 7 of 4 and log base 7 of x, making it log base 7 of 4x, because we're allowed to multiply when we're adding. And then because it's log base 7 of 4x equals log base 7 of 12, I can drop the logarithms and say that means the arguments then have to be equal. And so then x has to be 3. And since x is positive here, and that's good, then I can say that is not an extraneous solution. That is the answer. All right. Here, I'm going to go log base 2 of x minus 6, and then I'm going to bring over log base 2 of x minus 4, make it positive, and that's equal to 3. So I get log base 2 of x minus 6 times x minus 4 is equal to 3. Okay, then I'm going to just jump over here. Now that gives me log base 2 of x squared minus 10x plus 24. I expand that, and that is equal to 3. Then I write it as an exponential. So I take 2 raised to that power is equal to that argument. So I get x squared minus 10x plus 24 is 2 cubed. So that means that x squared minus 10x plus 24 is 8. If I then subtract 8, I get x squared minus 10x, and then 24 minus 8 is 16. So that gives me x minus 2 times x minus 8, if you factor that. And that gives me two possibilities. X is equal to 2, or x is equal to 8. And then I just have to check them. And if I go back here, and I'll just do it in the different colors so you can see what I'm doing. If I put in 2 minus 6, I'm going to get negative 4, and that's not okay. So this x equals 2 is not big enough. It's not okay. It's not a good solution because it's going to end up giving me a negative logarithm here and also here. If I go 2 minus 4, I'm going to get minus 2. So I'm going to take the log base 2 of minus 2, and I can't do that. So this one is extraneous. This one's okay, though, because, again, if I do this in a 8 minus 6 and 8 minus 4, they're positive. 8 minus 6 is 2, and 8 minus 4 is 2. So that's okay. But this is not. Now, the last one here, it's already solved as an exponential. So I'm just going to go x minus 8x, and then it's to the 5th power. So I can do this, and I'm just going to show you this. I'm not going to further this. I want to show you something else that might make your life a little bit better. But if I did this, that's a problem because I'd have to expand x squared minus 8x to the 5th power, which is going to give me a lot of terms. And then I have to know what 3 to the 10th is. And I say, yeah, I'm not really sure I want to do that. So I might be stuck. So what I'm going to suggest you do instead, okay, is we're going to try to make our lives better using the rules for logs. The rules for logs say that I'm allowed to bring that 5 down in front of the logarithm. So I can write it like this. And then I'm going to divide by 5. So that's going to make it log base 3 of x squared minus 8x is equal to 2. Okay, if I divide them both by 5. So this is divided by 5, and so is this. All right, then I can write it as an exponential. So now I can write it as an exponential and make it x squared minus 8x is equal to 3 squared. Base raised to the power equals the argument. So that means I get x squared minus 8x is equal to 9. Which then means that I have x squared minus 8x minus 9 is equal to 0. I factor that and get x minus 9 times x plus 1 is equal to 0. And that gives me two possibilities. Either x is 9 or x is minus 1. Okay, and then I have to go back up and check to make sure that this works. And what we mean by work is it can't give us a negative value up here. It can't give me a negative number in there. So I'm going to check that. All I have to check is this. All right, I just have to check that x squared minus 8x and see if it's negative. So if I do x squared minus 8x, if I go 9 squared minus 8 times 9, that's just going to give me 9. If I do minus 1 squared minus 8 times minus 1, I'm also going to get 9. So that means they both work. They're both solutions. They don't give me negative values, so I say they both are okay. All right. If either one of them was negative, they would not be okay. And that's the important thing to understand. So we're going to stop there in terms of just solving log equations, and then we'll do another video which shows you. Actually, no, you know what? There's only a couple of slides here, so let's just do them now in the same video. You can pause it and practice all the way through. But so let's look at what happens with exponential equations. So you might say, well, okay, we know how to solve log equations, but what about if I never have a log equation? Okay, one of the biggest uses of logarithms is actually to solve exponential equations. So you remember when we were doing exponential equations before, we said try to get the base to be the same. And the thing is, you can't write 4 to some power to give you 605 in this case. So whenever you can't do that, whenever you have an exponential equation where you can't find a similar base, we use logs. And we use logs because if you take the log of both sides, what the log rules say you can do, and this is what's important about this and why it's helpful, is you can actually bring the exponent down. So I can write this as x log 4 equals log of 605. And then I can solve that for x. I can say x then is log 605 divided by the log of 4. And while neither of those numbers is nice, and probably the answer isn't nice either, we know that because if it was nice, we'd be able to write 605 as a power of 4. You can get an answer from your calculator because you have a log button on your calculator, all right? And I'll just show you, I think this calculator is a log button. Yes, it does. So I'm going to go log of 605 first. So the log of 605 is about 2.78. I'm just going to write that down, 2.782. And then we're going to divide that by, if you have a calculator that allows you to, I would encourage you to put it all in at once. But I'm just going to show you each of the numbers. Log 4 is 0.6021. And then obviously this answer is going to be slightly rounded off, but 2.782 divided by 0.6021 gives me about 4.62. Okay. Now, you can check your answer just like any equation, because I can take 4 and raise it to the 4.62 and see if it gives me, it's not going to give me exactly 605, okay, because I rounded off. So it gives me 604.6682, but it's basically 605 if you account for round off error. So that's how you can use exponential equations and logarithms together to solve for things that otherwise we would not have been able to solve for. And that's really the greatest use of logarithms, is actually in solving exponential equations, because we've seen applications of exponentials all the way through the last couple of videos. We've seen them. And so we want to say, okay, well, if we can apply exponentials to all sorts of different places like radioactive decay and like half-life and population growth and all those sort of things, and even money and interest and that sort of stuff, that's where this logarithm thing is helpful. So let's just do a couple more examples of this and then we'll call it a day. So here's a question where I have 4 and 3. I have different bases. So I'm going to just put a log on both of them. Log 4 to the 2x minus 1 is equal to log 3 of x plus 2. And then I'm going to bring the exponent down. So I'm going to have 2x minus 1. Okay, log 4 is equal to x plus 2 log 3. All right, and then I'm going to expand. So I'm going to get 2x log 4 minus log 4 is equal to x log 3 plus 2 log 3. Keeping in mind that these are numbers. Log of 4 is a number. It's not a nice number necessarily, but it is a number. So I'm going to bring my x's together. So I'm going to bring my x's that way, and I'm going to bring the log 4 then that way. So I'm going to get 2x log 4 minus x log 3 is equal to 2 log 3 plus log 4. All right. And then if I just go up here to finish, I'm going to factor the x out of the left-hand side, and I'm going to have 2 log 4 minus log 3 is equal to, and then my right-hand side I'm not going to change, 2 log 3 plus log 4. And then I'm just going to divide. So x is going to be 2 log 3 plus log 4 divided by 2 log 4 minus log 3. And at this point, we're just going to take our calculator and say, what does that give me? And I'm going to use my calculator that I'm not using the one on the computer because it doesn't allow me to do this all at once. So I'm going to use my calculator that does. And I would encourage you to use your calculator as well and just see what you get when you do this. Okay, so I'm going to tell you my answer in just a moment. It's taking a little bit of time to type this whole thing in because it's a fairly large equation. But you find your answer as well while I'm doing it here and see if you get the same thing as I do. I'm getting 2.14 on my calculator after all of that. And again, you can check your answer if you go back and do that. I'm not going to at this point just for sake of time. But the same thing is going to happen down here. So rather than go through another example, I'll just leave it at that. You can try that one on your own and get the solution from your teacher. But hopefully that makes sense. It's a long video, but it's important that you understand all these different applications of logarithms. So we'll stop there and you can practice on your own.